I am about to get buried in concrete. And while that's happening, I'm going to explain everything you need to know about this substance. So the first thing that I want to clear up is the difference between cement and concrete, because people often mix these up, okay? Cement is like the glue. It's the matrix of stuff. Oh, there, I feel it. Okay, that feels good. Now, concrete is cement plus aggregate, so plus gravel and sand, and this is filling up really rather quickly. Cement is the most important man-made substance on the planet. We use more of it than any other substance apart from water. Every year, 500 kilograms of cement are created for every man, woman, and child on Earth. And that amount of cement can make 2 cubic meters of concrete, which is about 2 of these big fish bowls.
This video is sponsored by Ren. I don't think people realize just how important concrete is, so here's another way to think about it. Every year we make a certain weight of goods out of copper, more out of aluminum, and then you have glass, asphalt, lime, iron is a big one for all the steel, and then there's ceramic and wood. But by far, the solid product we make the most of is cementitious material, essentially cement. We use as much of it as we do all other materials combined. And it's easy to see why. Concrete is liquid rock. You can pour it into any shape you like. It's strong and durable and inexpensive, and it is so easy to produce that people have been making a version of it for thousands of years. To make primitive cement, the key ingredient is limestone, which is basically calcium carbonate. If you heat it up to around 1,000 degrees Celsius, that drives off CO2 out of the rock, leaving calcium oxide, which is also known as quicklime. Now, if you grind up the calcium oxide and mix it with water, you get an exothermic reaction that creates calcium hydroxide, which you can pour into a mold, and over a time, it will absorb CO2 from the atmosphere, turning back into calcium carbonate as the water evaporates. Now, that's a pretty good primitive cement. It's the first way that people ever made cement, but there are several drawbacks to it. I mean, for one thing, you can't make the molds very big because otherwise CO2 can't penetrate all of the material and harden it. Plus, it's not going to work underwater where there is no CO2 to harden your mixture. The Romans discovered the solution to these problems. They added volcanic ash called pozzolana to the crushed limestone before heating it up, and they discovered this cement was much stronger and much more durable. They used it to create the largest unreinforced concrete dome in the world, the Pantheon, which has stood for 2,000 years. And they built concrete piers into the sea, which hardened underwater, some of which are still standing today.
I did not expect it to feel this heavy. Like, it's already really weighing down my feet and making me slightly concerned about being able to get out. What I can tell you is that concrete is about 3 times as dense as water.
Are you able to lift the leg? I just want to make sure that you're not going to have some suction.
Yeah, okay. I'm going to try to lift a leg just to see how bad it's going to be. What I like is having my feet on the bottom, and I'm not sure I can get them back down there after I lift it up, but oh boy. Okay, so that was I'm going to try to lifting this leg pretty slowly, and I was able to lift it. Right. So at least up to this point, I am able to get out.
My fear is that the concrete is so dense that when it gets up around my chest, it may apply a lot of pressure, making it hard to breathe.
It's like being in a trench and having to cave in on you. You cave in your lungs so you can breathe. Because once they contract and the weight gets against your lungs,
that's going to be hard.
Have you thought about that?
Well, now that you mention it. But we do have oxygen on hand just in case. Earlier, I practiced how I could get out of the bowl if I'm in trouble.
Do you feel that's okay?
That's no problem.
Okay, great.
So how did Roman concrete harden underwater, and in thick slabs that CO2 couldn't possibly penetrate? There is a claim that it was superior to modern concrete. So was it? For centuries, the Roman recipe was lost. It was only discovered in a book in a Swiss monastery in the 1400s. And since then, architects, scientists, and engineers have been experimenting with different cement recipes to try to achieve the best result. Now, it turns out that that incredible strength, durability, and ability to set underwater of the Roman cement, that came from the pozzolana, that volcanic ash that was added. And nearly 2,000 years later, people discovered that adding clay or shale to the limestone before it was crushed and heated produced the same effect. And the reason is that all of these materials contain silica. And silica totally changes the chemistry of the cement. It means that it doesn't need to dry in order to harden. In fact, the water becomes an integral part of that hardened concrete, so that it actually achieves maximum strength when it sets underwater.
So this is the compressive cylinder curing room. We're required to maintain the concrete samples in 100% humidity, so we've chose to submerge them in water in a lime bath.
Every time concrete suppliers pour concrete on a job site, they cast sample cylinders of the material so they can later test it to ensure it has the strength required.
So we actually intercept a little bit of the concrete going into whatever structure they're pouring, a slab, a wall. We'll intercept it into a wheelbarrow, take the wheelbarrow over to our testing station and start casting these compressive cylinders. Every day we're breaking these cylinders, checking it for strength. You can see these have been broken today.
This strength increases over time, so samples are tested at 7, 14, and 28 days when the concrete is said to have reached full strength.
So what we do is we list the date that there will be placed in the compression machine on top of every cylinder.
In reality, it will continue strengthening after that. Samples are placed in a hydraulic press, and then the pressure is increased on them until they fail.
All right, ready?
Yeah, let's do
Start
it.
loading. Sure. We want to maintain around 30 psi per second.
And it's important to load at that rate.
Yeah, you don't want to shock it. You don't want to shock it by applying too much load too fast. This middle number is showing us our strength in pounds per square inch. And then the top number, the big number, is showing us the force of pounds we're applying.
What are we going to get up to, like 7,000 psi?
10,000.
10,000. So this is going to be really strong.
Very strong.
Okay.
Yeah.
It's always fun when we get something over 10,000. Like a free show. Bang!
It'll shake this room. And these are reinforced concrete walls.
It's amazingly just like you can't see anything happening, even under all that pressure.
It's still holding.
I know, right? It's
Oh, here it goes.
starting to dry.
Really?
There it goes.
11,000?
Mm-hmm.
Over 11,000 now. Oh yeah.
You've been filming a lot, haven't you? You didn't even budge at all. That's my favorite part.
That's cool. Yeah, I like that.
Like the strongest concrete in the world.
Well, the strongest concrete in the world is going to be like a lab-only thing.
In a competition was above 100,000 psi.
Today, virtually all concrete is made with a cement formulation discovered in the 1840s. It's known as Portland cement. But the name is really just a marketing term. You know, they claimed that the gray color of the cement would resemble these very desirable rocks which were quarried near the town of Portland, England. But the Portland cement was made by crushing up limestone and then mixing it with a certain percentage of shale or clay to provide the silicates. And then that was all ground up into a fine powder and put in a kiln and heated to very high temperatures. And what comes out are these nodules that are really hard. They're called clinker. Now, it's suspected that cement chemists in the past may have produced clinker by accident when they overcooked their lime mixtures. But since this clinker is so hard to grind down, they just considered it waste. But if you do grind it down, the cement that it produces is far superior to basically any other chemistry we've discovered, which is why it is so commonly used today. Now, there are lots of compounds inside Portland cement. The most common one is tricalcium silicate.
I'm now feeling incredibly buoyant. Like I am now floating in concrete, which is pretty ridiculous because most of my body is out of the material, but because it's 3 times as dense as water, you can float just up to your waist. This is totally unexpected. I did not expect to be able to like float in concrete. My feet are off the floor. That's where my feet are. My feet are here and my shoulders are up and I'm just being pushed up out of this.
Once you have the cement powder, the other things you need to make concrete are the aggregates, sand and gravel. These are blasted out of a quarry. Then they're ground up to be particular sizes. There are very strict requirements about the sizes and shapes of the aggregate which is going to get poured into the concrete, because of course that will affect the strength of the concrete that results.
Yeah, this is just a well-graded concrete sand. The most well-rounded material helps the contractor as far as their finishability goes.
Yeah.
You know, when they're running that trowel over that slab, they want a rounded particle, not a jagged, crushed particle.
Do you really want like a spherical sand?
A rounded, yeah, spherical sand, like a river stone, like a river sand. Designers on the strip want to pour concrete elevated. They want to lighten up the load of the deck. We'll incorporate some lightweight aggregate in place of this normal weight. 3/8 size. Typical concrete will weigh 150 pounds per cubic foot, normal weight. This gets us about 110 pounds per cubic foot.
The aggregates are hauled to the concrete plant in big trucks.
All right, I'm gonna release the rock.
Where they're dumped. And then they travel on big conveyor belts up into storage piles. These get loaded into big hoppers and then weighed out and poured into the trucks.
The control operator is going to open this gate and drop material into this hopper down into the mixer truck below. This is where the batch operator's controlling the plant. Right here in front of our batch operator, William, is the actual recipe that he's going to dispense into the concrete mixer. Each line represents a different component in the concrete. That top one there is a 3/4 rock. We have an intermediate 3/8 rock below it. There's your sand. Over here in this column, he's targeting, for instance, 3/4 rock. He wants to hit 13,000 pounds of material for that load. The computer is going to try to hit 13,042 pounds of 3/4 rock.
So everything's filling up
right now.
Now, if he goes out of tolerance and he overshoots a target, it's going to change to red, a red color. Up here on this screen, we're actually showing the holding hopper. This material he's weighing is directly above the mixer truck that just pulled under the plant. What about the water, William, being orange?
Yeah, we're a little under on that.
But we can always add a little water.
Yeah.
We cannot take it away.
All right, I'm gonna take a look inside the truck here. That's what it looks like down inside a cement truck.
So I was interested to see what would be the difference in strength between pure cement, cement with sand, and cement with sand and gravel, like the typical concrete mix that they would make. So I had them make up these special cylinders and test them in the hydraulic press. You might think that since pure cement has the most glue, it would be the strongest.
Cement's the magic, right? The glue. So if we lessen or lower the amount of cement per unit volume, we're going to have less strength.
But when we tested the pure cement cylinder, it fractured a lot as the load was applied.
Is that it?
No, let's let it keep going. It can take some more pressure.
What?
8,000 PSI, now it failed.
Now, cement plus sand.
9,163 PSI.
Edit the prediction. My prediction was based on the strength it was 2 weeks ago, which we have here. We got 14 days of 6,600, so reason would be it'd probably break another 1,000 PSI above that, but it definitely gained a lot.
And finally, cement plus sand and gravel. This is the normal concrete mix.
Is that it?
No. Part of it.
Whoa. Okay, so that's it.
That's it.
Okay.
That's it.
So it did fail at 8,300. Okay.
I was surprised to see that all the cylinders broke under about the same pressure.
I think to me really interesting that you could have all of that cement, right? But you don't get appreciably
Right.
stronger than like this or that.
Cement is the most expensive part of concrete, so if you can get away with reducing it down to 30% in the mix and still get the same strength characteristics, well then you should definitely do that. The other thing that was interesting was pure cement seemed to flake and chip more as it was loaded. So it seemed like adding the aggregate actually helped the sample cohere and stay together even under all that load. So was Roman concrete superior to modern concrete? Well, the answer is no, in short. I mean, there were some surprising advantages that Roman concrete had. For example, it was actually less well mixed than modern concrete, so there were little blocks of undissolved calcium oxide, or quicklime, that remained inside Roman concrete. And then what happened is, when the concrete cracked and water got in there, it would dissolve that calcium oxide, forming calcium hydroxide, and then you would get the new growth of calcium carbonate. So Roman concrete was actually self-healing. That's kind of a fascinating advantage. But I would say, by and large, when we look back at the Roman structures, we only see the ones that have survived to this day, so there is a survivor bias. And finally, there's the issue of cost. We could make very strong concretes that could last an incredibly long time, but we choose not to, because it's just cheaper and we don't expect our buildings to last that long. Before the concrete goes out on site, they have to make sure it's the right consistency for the customer, not too dry and not too runny. This can be adjusted with water, but you don't really want to do that because that can also affect the strength. So here, they use modern chemicals like superplasticizers.
So up here on the top left, you have our dispensing units for all our chemical admixtures.
And that's what they're adding now, a superplasticizer. It makes the concrete easier to work and spread around without really changing the water content very much. To check that the consistency is right, they perform something called a slump test or spread test.
We're gonna fill the cone to the top, nice and level. And we're gonna pull that metal cone off, measure the distance it travels on the board.
The concrete they're pouring on me should have a spread of 27 inches.
We're gonna measure it both sides. Woo! Right on a 27 on that one. Then go this way. Right on a 27 on that one.
So why is it so important that you got the right consistency of concrete?
You don't want it too dry. You want it wet enough to flow and fill up whatever container you're trying to fill. In this case, the sphere with you in it.
So the question you're probably wondering is, how long can I stay in here before the concrete hardens? And the usual answer is about 4 hours without agitation. And that's why when you see concrete trucks driving down the road, that drum has to be turning to keep the concrete agitated and to prevent it from setting up. But what happens if the truck breaks down, or there's a traffic jam, or something breaks? Then at times, concrete does harden inside the drum of these trucks, and that is a terrible outcome. But there is one thing you can do to slow the concrete down from setting, and that is to add some regular pop, like Coke. The sugars inside this Coke actually prevent the setting up process from happening, and that can buy you a few hours. So apparently these truck drivers, they drive around with a few 2-liter bottles of pop inside their cab, and so they can dump it in their load if they have to prevent it from setting up. So hopefully that means I'll get out okay too.
But how does concrete actually harden? Well, you have the dry mixture of gravel, sand, and cement powder, and then you add water. The water starts dissolving these cement powder grains, so ions enter solution. And some of those ions are calcium hydroxide. So that's what makes concrete a very basic solution.
What do you see?
We're approaching 12, 11.8.
So the pH of concrete can get up to 12 or 13. The pH of this is 11.8. And that's incredibly basic, which means if it's on your skin, if it's on your body, it can be dissolving your skin and cells.
Being buried in concrete is sort of like jumping in a vat of bleach.
And that's why I'm actually wearing a dry suit and some latex gloves. Yeah, it's not something you want to try at home, so do not try swimming in concrete.
So now the ions are dissolved in the solution. And remember, the most common compound in cement is tricalcium silicate. As it reacts with the water, crystals start to form of calcium silicate hydrates, plus other hydrate minerals. And all these crystals grow and become interlocking, causing the concrete to harden. Note that the water is essential to the formation of these crystals. So water is not evaporating, it's not drying out, it's actually becoming part of the solid concrete material. And that's why this chemistry is called cement hydration. It's also why freshly poured concrete should be kept in as damp an environment as possible. Las Vegas is so dry they frequently set up misters to spray around new concrete to ensure the humidity was high enough. One of the things I realized while making this video is that limestone, the core component of cement and concrete, well, it comes from ancient sea life. Limestone is formed from the skeletons and shells of ancient sea organisms that, died millions of years ago, and then all of that got compressed. And now we use that to make huge skyscrapers and overpasses, basically every huge piece of infrastructure. It's made with concrete. And so now when you look at a beautiful city skyline, what you're really seeing is ancient marine life. Skyscrapers are made of seashells.
Skyscrapers are made of seashells. Skyscrapers are made of seashells.
Yeah, this is wild. This is hilarious. I have no words.
I'm trying to push myself down into it, but it's it pushes me up. I'm pushing down into the concrete, but it's well, I'm getting pushed out of this thing. I'm just gonna try to push myself down in here. Ooh. That is it. There is no, you cannot get buried in concrete, okay? I'm doing my best right now to sink down, and it is not happening. But I'm gonna use my arms to push myself in. Oh, working against buoyancy, this is hard. We were worried about getting me out, but I can't stay in. I'm gonna try to jump in. Here we go. That's it. All right, here we go. 1, 2, 3. That's great. Oh! That feels so good. I don't want to get out. This is so nice. Does anyone got a time check? This stuff is not going to set up on me, is it?
So as we've seen, concrete is one of the most important materials in the world. It's made possible most of the large-scale infrastructure we rely on. But it also creates a lot of CO2, an estimated 8% of the global total. That is more than the entire aviation sector. But together, we can do something about that. I would personally like to offset 1 month of your carbon emissions, and I will do that through this video's sponsor, Ren. Ren is a website where you can calculate your carbon footprint, see which aspects of your lifestyle make the biggest contribution, and learn how to reduce your impact. And then, if you like, you can offset your carbon footprint by funding a diverse mix of carbon reduction projects like tree planting, mineral weathering, and rainforest protection. For the first 100 people to sign up, I will personally offset your first month of emissions. Just click on the link in the description. Now, I don't think we're going to solve climate change using individual action alone. If you can change your light bulbs or install solar, that is great. But what we really need is change on a systemic scale. And that's what I like about Ren's approach. They not only plant trees and protect rainforests, they also support policy groups lobbying for change, like the Clean Air Task Force, which advocates for new technologies and policies to get to a zero emissions economy. The way I see it, there are moneyed interests lobbying to keep things the way they are. So we need to band together through organizations like Ren to lobby for change. And if you agree with me, then I invite you to click the link in the description and join me in offsetting our carbon emissions and investing in large-scale systemic change. So I want to thank Ren for sponsoring Veritasium, and I want to thank you for watching.